Have you ever stopped to wonder what gives a trampoline its bounce? Or, why a guitar string even makes a sound? Well, the answer is this incredible hidden property that governs pretty much everything around us. Elasticity. It's this invisible force that dictates how things stretch, bend, snap back, or break for good.
Okay, so think about this for a second. It's a really simple mystery, right? You stretch a rubber band, you let go, and it snaps right back. But then you take a paper clip, you bend it, and it just stays bent. They're both solid objects, so what is the deal? What's the fundamental difference? Well, that's the exact question we're going to unpack today.
All right, so to solve this whole rubber band and paperclip puzzle, we first need to get on the same page. We've got to define what we're actually talking about when we say elasticity.
So here's the key idea. You can think of elasticity as a material's memory. It's this built-in desire of an object to go back to its original comfortable shape once you stop messing with it, once you stop pushing or pulling on it. The stronger that desire, the more elastic we say the material is.
Now, in physics, it really helps to think in extremes. So on one end of the spectrum, you have something that's perfectly elastic. A great example is a quartz fiber. It snaps back completely every single time. And on the total opposite end, you've got something perfectly plastic, like a lump of wet clay. It has absolutely zero interest in going back to its old shape. The thing is, most objects we see every day, they live somewhere in between these two ideals.
But to really, truly get why some things snap back and others don't, we have to zoom in. I mean, way in. The real secret to elasticity isn't something you can see with your own eyes. It's all happening down in the unseen world of atoms.
Okay, this right here is the single most important idea to get your head around. Just imagine that every single atom in a solid object is connected to all of its neighbors by these tiny invisible springs. Now, they're not real springs, obviously. They're just a way for us to visualize the incredibly powerful forces that hold all those atoms together.
So how do these little atomic springs work? Well, every atom has this perfect, happy distance it likes to be from its neighbors. That's its equilibrium point. If you try to pull the atoms apart, an attractive force kicks in, just like a stretched spring trying to pull them back together. But if you try to push them too close, this really powerful repulsive force shoves them apart. It's this constant microscopic tug of war that actually creates the elasticity we see. All right, now that we kind of get what's happening at the atomic level, let's zoom back out. Let's connect that microscopic push and pull to what we actually see in the real world. And that brings us to two of the most important concepts for this whole topic: stress and strain. You can think of this as a super simple cause and effect relationship. Stress is the cause. It's the force you're applying that stretches those atomic springs. And strain is the effect. It's just a measure of how much the object deforms as a result. So it makes sense, right? More stress leads to more strain. And you should know, stress isn't just about pulling something apart or squishing it together. Take shear stress, for example. This happens when you apply a force parallel to a surface, kind of like pushing the top of a deck of cards. The layers of the material slide past each other, which changes the object's shape, but not really its overall volume.
So what if you could visualize a material's entire journey, from the first time you pull on it until the moment it breaks? Well, engineers have this amazing tool that does exactly that. It tells the complete life story of a material under pressure.
And here it is. This is the stress-strain curve. I love this, because it's basically the biography of a material. Up the side, on the vertical axis, you've got stress. That's the force we're applying. And across the bottom, on the horizontal axis, you've got strain. That's how much it's deforming. Let's walk through this story together, piece by piece. The first part of the story is this initial straight line. This is the elastic region. Down here, stress and strain are perfectly proportional. If you double the stress, you get double the strain. That relationship is called Hooke's law. And if you remove the force anywhere in this region, the material snaps right back to its original shape, no problem. This is the rubber band's happy place. But if you keep pulling, you eventually go past a point of no return. We call it the elastic limit. Once you cross that line, you're in the plastic region. In this part of the story, the material has kind of given up on going back to normal. Those atomic bonds have started to slip and rearrange themselves permanently. If you let go now, the damage is done. The deformation stays. This is where our bent paper clip lives.
If you keep applying even more stress, the material eventually reaches its maximum strength, and then finally, it hits the breaking point. The story is over. The atomic bonds are just completely overwhelmed and the material ruptures. It fails. It breaks.
Now, of course, different materials have very different life stories.
Brittle materials, like glass or ceramics, have a really short and dramatic one. They stretch elastically for a little bit, but they have almost no plastic region. They just snap. But then you have ductile materials, like copper or steel. Their story is much longer. They can be stretched and deformed way into their plastic region, which is exactly why we can do things like draw them out into long, thin wires.
So why does any of this matter? I mean, who cares about these graphs? Well, understanding a material's story is literally the difference between a safe building and a total disaster. This stuff has huge, real-world consequences for engineering, for safety, for everything.
And one of the most important real-world concepts is something called elastic fatigue. You see, just like people, materials can get tired. If you put them through repeated cycles of stress and strain, even small ones, they can start to lose their elastic properties over time. This is why bridges have a lifespan and are eventually declared unsafe. It's why an old bathroom scale might start giving you the wrong weight. And it's exactly how you break a paperclip. Not with one giant bend, but by bending it back and forth over and over, fatiguing the metal until it just gives up.
So that brings us to one last really important question. If you're building a skyscraper, something that needs to be strong but also flexible enough to sway in the wind without breaking, what kind of material story are you looking for? Do you want something with a short, brittle story or a long, ductile one? Answering that question correctly using this hidden science of elasticity, well, that's what holds our entire modern world together.